Okay. Hello, everyone. This is the Julia for Economists session. This is going to be about how to kind of write performant Julia code. So I'm Cameron Pfeiffer, and you can email me here at cpfeiffer@stanford.edu if you need to, if you've got any kind of comments or questions or whatever. Okay. So I'm currently a PhD candidate from the University of Oregon. I nominally work in finance, but I end up doing a lot of other stuff. I'm visiting here at Stanford, and as kind of part of my time here at Stanford, I basically work on, like helping people do like big computational economics problems. And so we kind of thought we'd teach some Julia to economists while we're doing this. So you can find all these past lectures and recordings and notes on the GitHub repo, which is at C. Pfeiffer Julia Bootcamp 2022. And you can pull everything in here. So there's links to all the previous recordings, lecture notes, example data, project solutions, that kind of thing. So if you need any of that stuff, it'll be here. And then the recording for this session will also be in that repo. Okay, so we shortened the session so they're a little easier to attend. They're 2 hours now, so this is not going to be like a 4-hour thing. And today I don't have any problem sets because there's a lot of weird examples, and it's kind of hard, honestly, to cook up problem sets that people can like work through in a short amount of time, particularly for like performance heavy problems. So this will be like a lot of like going through very specific and interesting examples and showing you how they kind of impact performance. So you can ask questions when you need to, interrupt if you want to. And I'm going to assume for the rest of this that you have Julia. I'm going to assume you have some kind of binary or some way of running it, and a text editor, whatever format that takes for you. If you don't have it, then you can go get it at julialang.org/downloads and follow along if you want to. Okay, because I'll be running through some examples. Okay. So first we're gonna, I've got like a huge smorgasbord of stuff to go through today. So it's all just like the little fiddly bits about Julia and programming and how your computer works that make things slow or fast or whatever. So I'm going to talk a little bit about Julia's compiler. I'm going to talk about how to kind of reliably write fast code and like the big red flags to look out for and how to debug things. And then I have a bunch of other stuff here, right? So like I'll talk about like code analysis and doing some profiling stuff to make sure that you're, writing stuff at pace and like making sure that the compiler can like take your code and make it really fast on your behalf without you having to work too hard. So the big one here we're going to talk about probably is type instability. This is like Julia's like big, as a Julia programmer, this is the thing that you need to pay a lot of attention to. When you have very type stable code, Julia can do a lot of things on your behalf. And I just want to make sure to show you how to catch when you have type unstable code and how you can make it type stable. Okay. But this is just kind of a rough guideline of what we'll talk about. There's a ton in here. Okay. So the structure of this talk is kind of loosely informed by this performance tips document on the Julia Lang docs. So this is like a version of this document where I've added like some commentary and I've showed some benchmarking so that you can see the timing differences when you actually call a lot of this stuff. So yeah, this is if you want a version of this document that's not locked in a video, or a version of this talk that's not trapped in a video, you can go to performance tips and typically it'll give you all the information that you need to have. Okay. All right. So kind of the first place we're going to start here is with Julia's compiler. So you probably heard the word compiler. I've mentioned it before. I think, everyone just kind of like vaguely waves at this thing called a compiler. And, what it is a thing that takes human readable code. This is what you as a programmer write, and it turns it into a machine readable code. This is the thing that your computer understands. And, compilers are a way that you can like take what you understand about a language, and when you pass it through the compiler, you can use your understanding of that language to make things faster for the programmer. And so because there's a nice compiler between us as programmers and your computer, the compiler can take a look at our code and say, well, this is like maybe a little inefficient. I can do it this way for you. And it kind of gives us like little free speed boosts as it's compiling it down to machine code. So I'm going to take a look. I'm going to show you kind of the stack as we write our own code, and then how it goes through several layers until it gets to your computer, and your computer can actually like read it and input it and run it. So I'm just going to write this function, and it's called test function, and all it does is just add 1 to the argument. This is like a super basic argument, super basic function. Now there's this macro that we have, and a macro is a thing that starts with an @ sign. This is like a special, kind of a special function that can wrap whatever you put to the right of it in a bunch of extra code. So it just like, you can think of this as like putting a bunch of extra stuff around test function. And what this extra stuff does is it tells us what the specialized typed code is that Julia's compiler is making for us, okay? So code typed takes a function call and returns this kind of typed function by Julia. And so this is a really good tool to analyze what it is, like how Julia is thinking about your code. And so when I run this here, you'll see that when we call test function, what it's converting it to, what the compiler converts it to, is base.addFloat, whatever x is. So this is the input of our function, and it's just going to add 1, right? This is the exact argument that this is the exact function that we wrote. It's going to assign that some value to %1, which is a value in memory, and then it's going to return whatever 1 is, right? So this is like a really high level representation. This is not yet stuff that is going to your computer. There's a couple layers in between this, okay? The next layer down is what is called the LLVM. And the LLVM is like a suite of tools that, open source tools for like designing compilers, and it has its own compiler, and there's like an API and all kinds of cool stuff that you can use to do compiler stuff. And so it has this language independent intermediate representation, which is a level of a language that's in between what we write as programmers and machine code, which is what your computer can execute. So LLVM occupies this middle space. Okay, and so you can use @code LLVM to see the code that the LLVM is going to generate. And so it defines this function here that accepts a 64-bit floating point number, and then it's going to add to whatever that is a 1, and then it's going to return 1, %1, which is the value that we just added 1 to. Okay, super simple, not terribly complicated. I don't want you to focus on this. I just want you to show you that this is what's happening. And then lastly, we go from the LLVM to what is called native code. And this is commonly referred to as assembly for x86 CPU architectures. And this is what your computer actually sees when you execute it. It does move ADSQ, and it has all this memory pointer stuff. It's assembly. I don't read assembly, and I'm scared of people who do. But this is just kind of here to show you what happens when it reaches your computer. Okay. All right. So the reason I'm showing you this is because I want to show you what happens when you give it, provide different types of input to test function. What Julia does is when you give it different types, so for example, an integer and a floating point, those are, float 64, those are 2 different types. Julia will specialize, create new functions for those 2 different types of inputs. So for example, this top one here is what happens when I give it a floating point number. And this one down here is what happens when I give it an integer value. And so it basically at this level here, we see we've kind of got totally different code. So this one here is for integer addition. This one here is for floating point addition. And these are both totally different. So Julia creates new specializations of code for your 2 examples. Okay. So we can also do this with a character, right? Because addition is, if I add 1, the integer 1 to the character A, it will return the character B. And so I can, actually print out the typed code of this, and it's much larger, but this is a very different function because it goes and does a bunch of different stuff. These are all new specializations for the exact same function. All that's changing is our inputs. Okay. So the broad reason I'm telling you this is every time you give a function a new type of input, Julia has to compile a specialization. Okay. And so if the type that you give it is really precise, Julia can go get all of those very precise little subfunctions to do with those precise inputs. If you don't know what the type of the thing is, if it's very abstract, if it's like of type any or whatever, Julia can't do that specialization, and it can't make really fast code on your behalf. So when you're writing a bunch of Julia code, what you want to do is make sure that when you give variables to functions, that you understand the types of those variables. Okay. And then once you do understand those types, and once Julia understands those types, you get free code because the compiler can do a bunch of cool stuff for you. Okay. So this problem is called type stability, where when you don't know the type of a variable that's being given to a function, Julia just can't figure out how it should specialize a function. And so it has a lot of difficulty. And this is kind of a hard problem. So what we have to do as programmers is kind of help Julia understand what's going into a function so it can understand what's coming out of a function. Okay. So type instability, when you have functions that are not well understood, the types are not well understood, can cause a bunch of slowness because compiling can be slow when you have to give it a new type, but also because type unstable functions don't give you the free speed that you get from compiler optimizations when you know types for things. Okay. So I'm going to give you this example here. This is called bad function. And bad function actually looks really simple, right? This is like a function that seems like very obviously okay. And basically what it does is if x is greater than or equal to 5, returns a character A. And if it's not greater than or equal to 5, it returns the integer 10, 5 times 2. Okay. So that's all it does. It's either character A or the number 10. Now I'm going to use this code warn type macro here, and this gives you a bunch of annotations to highlight when it is that you have a function that is type unstable. So if you're trying to debug performance, generally a good idea is to call @code warn type on an input, and it'll spit out a little report that you can use to debug something. So let's, I'm calling it with the input 3. And when code warn type evaluates this function, what it's observing is, you'll see something very bright here in red. The body returns a type union character int64. So this function is type unstable because it could either be a character or it could be an integer. And Julia does not know ex ante what the type is going to be. So, it knows that it has a Boolean, it knows that it accepts an integer, but it doesn't know what the type is going to be from the output, given the types of the input. Okay. So type stability is like a huge pain if it appears anywhere inside of a function. And so let's make this function here called nested function. And nested function just calls bad function with whatever the input to nested function is. And now we have x, and then we're going to increment x by 1. So if x is a character, this is defined. This could be b, or this could be 11, right? Given using the output of bad function. But when I call code warn type with nested function, you'll see that it identifies in line 2, or in the second variable here, when I create after I call bad function. Now it doesn't know this whole entire nested function is type unstable because bad function is unstable. And so now you've kind of contaminated this bigger function with the type instability that you introduced in bad function. Okay. And you can see this when you call @code warn type. It doesn't know the return type of the entire function. That's what this body segment tells you. And it doesn't know the type of the local x, which is this value here. So if you're debugging type instability, you can look in the locals field to see if it was, type instability was introduced within the function or some point, later on in the function.
Wait, sorry, Cameron, can you explain that again? What does it mean to have the instability introduced later in the function?
So you can have so z equals x plus 1. This would be a place where you like carry forward more type instability. So you can have like this, in this case, the type instability is not due like the type instability. This is from maybe not a good example to diagnose this with. In this case, the type instability shows up in X, right? So we know that there is type instability inside of one of the locals X. If I go to the previous version, in this case, the type instability does not show up in any of the locals because there is no locals field here, right? We don't actually allocate anything within the function. We know that by the end of this function, it is type unstable, even though at any point within the body, we know the type of pretty much everything. It's just at the end of the output, we know that it's type unstable. Occasionally we'll see more examples of this. We'll see like, intermittent examples where like these are not typed, where you can identify within the body where things are type unstable. I don't know, that's kind of not a very good explanation.
No, that makes sense. I'm also I'm trying to understand what instability, like where this fits into the workflow. So I get the general idea of instability makes things slower. There's also like instability breaks like forward diff and other kinds of auto diff functions that we talked about last time.
Yeah.
Like how do you just like put these warn types every time you write any function? Is this like part of unit testing? Where does this fit in?
So where this fits in the workflow here, I'll show you I'll show you in the kind of the scratch pad here. So I'll make this unstable function here. So if x is less than or equal to 0, then we'll return 0. Otherwise, return x. Right. So this is kind of a classically unstable function when you call this with a floating point integer. And one way to do this is inside of unit tests, you can do unstable 1.0. And so at inferred basically says, does the type of the return value match what we thought it was going to be when you call at code warn type? Okay. And so when I include this here, we can see this. Oops. Actually, where is inferred? Is it F benchmark? Oh, sorry. Inferred is not not part of my like typical workflow.
No, this is great. I get to see how you figure things out.
Okay, there it is. Okay. Okay, so it's inside of test function. So if you call using test, and if you're writing a testing suite and you call at inferred, we'll note here that the return type is a float 64 because we called it with 1.0, so it's not less than 1. It's not less than 0, so it's going to return x, which is 1.0, and so that's a float 64. That's a very strictly a float 64. The inferred type. So when this actually hits the compiler, it thinks it could be either a float 64, which is x, or it could be an int, which is 0, the literal 0. And so when you call inferred, you can actually have it throw errors when the type is not inferred correctly. And this is actually a really, really good tool to use if you're going through and writing unit tests. I think it's kind of a pain in the ass if I have like production code, but definitely if you're writing kind of a like large production code, that's good. Or have a testing suite.
But this is different from the like code typed calls that you were just showing us, right?
Yeah. So this is different. So this calls inferred calls at code warn type on your behalf, and what it'll do is it'll scrape whatever this type is here to the right of body, and it'll say, is float 64, which is the return value of this, is it exactly equal to this?
Got it.
Yeah. So I'll do that on your behalf. Okay, that was a good question.
Thank you.
Okay. So type stability is kind of loosely defined. There's actually a good paper about this. Is when the type of a function's output is only defined by the type of the input and not the value of the input. So when Julia doesn't know the concrete type of a thing, the code touching that thing gets worse, right? This is kind of almost unambiguously true, but varying degrees of magnitude. So we're going to use this example that I just showed you with Shosh, which is maybe 0. And so when we actually run this kind of code warn type here, we'll see that it doesn't know the type. And that's because this thing right here, this 0, is an integer. It is not the float. If I did 0.0 or 0 point, that is actually the float 64 version of that. Okay. So when I call this with if I call this with an integer input, it's correctly typed, right? Because this is an integer. All of these things are integers. X is an integer. The type is always the same given the type of the input. But if you call it 1.0, there's a potential that it could output an integer rather than a float. Okay. So I'm going to save this benchmark here for a second, just to show you the type instability. And to at benchmark here is a function that basically calls the thing to the right of it a lot of times. It does a lot of statistical sampling, and it'll tell you how much allocations how many allocations happened, the timing on average, the range, mean, median, various statistical properties of your run, and it'll output a nice little histogram. You'll notice I'm doing $XS. What I'm doing here is actually, when you put the $sign in front of something to the right of benchmark, this is actually interpolating it, and it gives you a more accurate example. I'm not going to talk too much about this. Just if you're using at benchmark, just make sure you interpolate something that is a global variable, right? Because XS is a global variable. You want to put a $sign just before it to make sure that it's accurate. But it's not always going to be a huge pain if you just left out the $sign, but it is less accurate. Okay, so I'll show you more. We'll come back to that, and I'll show you exactly, put these numbers in context, this 24 microseconds. Okay, so let's fix this by making sure that the type of the output is the same regardless of whether X is greater than or equal to 0 if X is a floating point. So a handy function here is called zeroThing, which will attempt to return a value of 0 in the same type as whatever the thing is. So better 0 here. Now, the only thing I've changed is I'm using 0x, which says, go find me the type of X, whether it's float or int, and then return a 0 if that's the case here. And so now we can see the body is correctly typed as float 64. We can also call it with an integer, and it is also correctly typed. So now this function is type stable. Okay, so this is a good outcome here, right? When you see all blue, sometimes you might see yellow, which is like, typing is like a little uncertain, or I think it's like union missing nothing. But there's no red here, so that's good from a type stability perspective. The compiler is generally able to understand what's going on here. Okay, so now let's benchmark this, so you can see how quick better 0 is. So our median time here is 1.389. And if we go all the way back to our bad sample, this is like 24 orders of magnitude worse. Almost, 20-ish, 15-ish, something like that, right? This is a extremely slow to do this with the type unstable function. And this is the most simple thing, right? This is like just like give it a 0 or the value itself, right? That's kind of hilarious, how much performance improvement you can get. And if you're calling this function millions or billions of times, that really, really starts to add up. So, this type stability thing may seem, fairly small because these are microseconds, right? They don't really, they're tiny, right? We can't even really comprehend them. And, but tens of thousands, millions of billions of times calling these functions, it's a huge pain. So definitely important to have kind of type stable code. Okay, so if you're going to handle type instability, you can use that code typed to chase down typed instabilities, or code warn type. Let me change that. And then you can also use these zeros return type to get the correct zeros for your type. And if you're working with like arrays, use zeros, type of thing, and something like this, right? And this will actually like pre-allocate for whatever the type of your input is, right? So if thing is an integer, then this will actually like give you an integer array rather than a float64 array. Okay, so just make sure that whatever you're returning is the type of the thing that you actually want it to be. Kind of like a commonly good tool here is called Traceur, which is a package which basically goes through this performance tips document that I flagged, and it just tracks them down for you and gives you a bunch of warnings. So if you want to use Traceur, you can call it with @trace just before whatever your function is, and it'll give you like kind of a detailed report. So you can install it with add Traceur. I'm not going to like go through it a whole bunch. I'm just going to kind of show you a little bit. But here is the same type unstable function that we were using before. And when I call trace before it, it'll say this returns union float64 and 64. And this is a good way of saying, oh, okay, maybe I need to actually dig into this function a little bit more. So if you're trying to like, if you're going through a big code base, you can just add @trace before your function call. And hopefully you'll get a warning that'll tell you, oh, this is maybe a little type unstable. Okay. So that's a handy tool to have. But Traceur can be a little slow, especially for very complicated and messy functions. Okay. Yes.
Could you say a little bit more about how to fix this? So like with the 0 example, that made sense. But for like complicated types, like I often have functions that return different kinds of arrays and things like that. And I find it challenging getting the types to work out. Are there any resources or rules of thumb for how to fix that?
Yeah, let's see if you have like here, sorry, let me actually just do this with a oops. Actually, yeah, let me do this with a code-born type. Okay, so this example here, I'm actually I have the literal 5, but I'm still constructing the 0x. So when this sum happens here, it does type promotion for us. So it sees, oh, okay, I'm adding a float and I'm adding an int. Well, the result of this is going to be a float because the float generally carries more information than does an int. This is kind of like a convention we've agreed to. So if you needed to shift this by some amount, you can do the addition here. And this addition is type stable because it is well defined for float64 and int. And we know the type is going to be float64 after this addition. As for kind of, more complicated issues, there's not really like a, it's always hard to debug type instability. So sometimes it's really easy. In this case, we just have to, add a, something that is a float64 inside of this so that it knows that this 5 should be converted to a float64. I believe you could also do convert float64 or something like that. I think that would be.
Are converts expensive operations?
I actually don't know. I don't think so. It's probably like, this is a pretty common operation. It's probably also what happens for inside of the sum call when you add them together.
Is it generally good practice? So like I know that when we were talking about declaring types in like functions or structs, I initially thought that was a good idea, and you sort of made the case that it's maybe not a good idea to have very specific types.
Oh yeah, I have a whole little section about that a little later.
Okay, I was just wondering if is there like a general rule of thumb where it's better to be explicit whenever you're uncertain about type instability?
Yeah, being explicit does help sometimes. For example, you could also do this. Oops, sorry. Oh, that's right. Yeah, that won't do it because it's just an assertion. Yeah, I'll talk about how to be explicit and how to be intelligently specific. Probably the better way to do this is like convert type of X, like that.
So or when in doubt, the convert type of X usually works.
Yeah, like if you know that the type of the thing is, another way to do this is to extract the type parametrically and just make sure that it matches over here. So this is an alternative way to do this that is type stable. And then this, when you do this, you don't actually have to do this function call to get the type, which can be like mildly, very lightly expensive compared to like the whole cost of this function. When you do this kind of parametric typing, sometimes it's easier to just like pop the type out when you do the function call and then just, stick it right here. So that's one way to do this.
Thank you.
Yeah. Okay. So actually, this leads really nicely into this. There's a bunch of super types that are intended to describe types of variables, right? So for example, string, this string howdy partner and this int 12 are both subtypes of any. So any is a master type that describes every single type that is inside of Julia. You cannot construct an any, it's an abstract type. But when you put these all, if you were to try to put this string howdy partner and this integer 12 into an array, the array has to have an element type that all elements are subtypes of. And so what that means is when I create this array, it's actually going to create an array of type any, right? So here I'm just adding a 12, this is an integer, a string, and then this one here is a float 64. So I can also just kind of print out the array here so you can see what it looks like. And you'll note that it's a vector any. This is a huge problem, right? Because, first of all, this is just a weird array. It's, you might do this in like Python or something where you just like mix types happily because it doesn't, it's just Python. But in Julia, it's kind of a huge pain when you mix these together. Because when you have a vector of type float 64, Julia can do all kinds of really cool stuff with that. It knows that every element is going to be at most 64 bits. Whereas in this case, strings are kind of theoretically unbounded in size, right? So you can kind of allocate a whole bunch of space to strings. Whereas, this is only ever going to be 64 bits. And so when Julia is doing the memory allocation for this, it has to do it really stupidly. And at the same time, because when you're doing, if you call any kind of function on this array, it doesn't know which function to dispatch to. So it ends up going to these really basic, really clumsy defaults. Okay. So this is an example of a thing that is bad. Okay. Abstract typed arrays are bad. So arrays that are not specifically typed can be really, really inefficient. And so, if you tell something that's float 64, it can assign blah, 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 all kinds of storage, and it can do all kinds of fancy math when Julia knows that something only has float 64s in it. If you give it an any array, it's, going to have a ton of trouble. All right. So I'll show you an example of this. So the first one here is I'm creating a matrix, and then I'm just, forcing it to be of type real. And I'm just putting some random numbers in here, and I'll actually just make this the same numbers for both. Okay. And on the bottom here, when we do this matrix multiplication, just matrix times itself, it has to do all of these allocations. It has to use up a bunch of time in memory. It takes almost 3 seconds. Whereas when I have it be exactly float 64, this is a concrete type, and this is an abstract type. The concrete type actually gives us way, way faster math. It just, it's not even close in terms of speed. So you always want things to be as concretely typed as you can when you're doing math on them. Okay. So this is an example, a motivating example of why it's really important to not use abstract types. Okay. So you might be thinking, gosh, Cameron, I'd never do this. I'm a top-notch code cowboy. And you might be right. Like maybe you never do this. Like maybe you never have these like any arrays or real arrays or whatever. Maybe they're always float 64, or always strings, or always exactly what you think they're supposed to be. But if you ever do this, where you start and just put 2 empty brackets, you're already screwing it up. So I do this a lot myself, sometimes because I'm really lazy and I have just code that needs to go that's not performant. But if you're trying to write performance code, you should not be doing this. So, and the reason is that when you leave, oh, I forgot to put this GIF in here. You're a bad boy, don't do this. When you do this, when you put these empty brackets here, it defaults that array to of type any because it doesn't know what you're going to put in there. It can't know your intentions. So if you know, for example, that it's going to be an array of only float 64s, you can type it ahead of time by putting the type right before the brackets. If you don't know it's exactly float 64, but you have something available that is the return type that you want to store it in, you can use type of a thing right before the brackets as well. That will also type this kind of empty array. Alternatively, if you know the size, just pre-allocate the whole array. And you can do this with array type of a thing. And then you put undef, which is a special keyword right here in the first argument. And then you put the size of the array in the rest of the space. This one is kind of the optimal, right? If you know the size of, how many things you're going to store, it's best to just pre-allocate the whole thing. This is if you don't really know how many you're going to have, but you know the type. And in general, you as a programmer probably do know the type. And you should be typing your arrays and not just be typing empty brackets, because that's just, you're going to have all these arrays of type any floating around in your code, and that just gums up the works like nothing else. Okay, so in this case, I wanted to kind of, actually here, let me separate out these code blocks a little bit so we can actually read them. Okay, I'll actually stick with the notebook view here. Okay, so let's see an example of how you might operationalize this. Okay, so what I'm going to do first is I'm going to have this array, this function called do stuff, and all it does is it accepts some input x. Note that this is not actually strongly typed. Julia will specialize this on my behalf, whether it's integer or whatever. It'll store whatever the input is in a name tuple. It'll store the sign of x, and it'll store that version that x converted to a string. Okay. So here I'll actually run this function for us so we can see what it looks like. All right. So we can see that this is a name tuple here. And I'll spit out the type so we can see what that looks like as well. This is a name tuple. Name tuples are really, really nice things to return because they're very concretely typed, right? They store the type differently for each element inside of them. So this one says this return value is float string. So this whole thing is very type stable, right? And we can verify that if we wanted to with that code warn type. Do stuff 1.0. And we can see it is going to return this name tuple here, which is what we just found. Okay, so that's good. We're rocking along. This is like a nice function that we're going to end up using a lot. All right.
Wait, sorry. Can you explain why that happened? It was named because you had the sign, or how did it know that the first two were how the first one was a float?
It knows the first one's a float because that's the type of the input. So if I change this to 1, the type is now actually going to be int64 float 64 string.
But this is considered type stable, even though it depends crucially on the input.
Yeah. So it has to. So type stability means that it depends on the input. It only depends on the input, the type of the input, not the value of the input. So sign of an integer is always going to be a floating point number. That's just well known. So if you give it a float or if you give it an integer, it's always going to return a float. So this function is type stable. This function, I'm just asking it to create a string. I always know that this is going to be a string. And this will return, if I give it an integer, we'll call the specialization of this function for the integer, and that will always return int float string. Whereas if I call it with a floating point, that will call a different specialization that is type stable, even though it gives me a different type. But the type depends on the type of the input, and that's what type stability means in this case. Okay. So let's kind of take a look at how you might consider doing this in the dumb way. So the dumb way here is I'm going to get some numbers, x's. And I'm doing the bad guy thing. Cameron, you are a bad man. Okay, right? So don't ever do this. I don't want to see people doing this. Unless you genuinely don't know the type and you really just need it to be type any. You're just putting like a bunch of crap in here. That's fine. Just don't tell me about it. It'll make me hurt. So what I'm going to do is I'm going to go through each element in XS. I'm going to call do stuff. This is going to return a name tuple, which we know the type of. This is a very strongly typed input given the type of X. And then I'm just going to stick it on this array. And then what I'm going to do is call map reduce. I'm going to go through each element of each name tuple here, get the sign of X, and then add them all together. So this will return, sign X. You and I know that sign X here is actually a float 64, right? So if I'm adding a bunch of float 64s together, this entire thing here is going to be a float 64, right? That's, we can just kind of read this, but Julia will not be able to figure it out because it does not know that everything inside of array is a name tuple where sign X is a float 64, okay? So the good way to do this is let's just call do stuff with the first element of XS. Let's just like run the first one so we can see what the type is going to be. And then let's stick it in the array. And you note here, I haven't put anything to the left, right? So this is, this is like, I haven't typed like float 64 or something here. But if you give an array, if you put brackets around something with an element, with a thing in it, it will type the entire array with whatever the type is of the first element, or, of the only element in there. And then I'm just going to go through all of the rest. Note that I'm starting from second to end. And then I'm going to do the exact same thing that I did up here. I'm just going to stick it all on array. And then I'm going to do the same map reduce call here where I'm just going to add up all the signs together. Okay. Now, let me do the interpolation here. Okay. And so while this kind of benchmark runs here, all we're doing here is I'm creating 100 elements, 100 randomly drawn normals. So these are all going to be float 64s. So we know that XS is float 64. So we know that for each call of do stuff, X is float 64, this is float 64 string. Okay. All right. So now that we're looking at our results here, oops, we can see here that the bad arrays version, this is the very type unstable version, gives us 55 microseconds. This one's 46 microseconds. So that's a non-trivial percentage increase just from not typing this array. You can imagine this, from much larger arrays, this being a bigger pain, but it's just kind of, it's important to note that this caused a lot of performance loss just from allocating this array this dumb way. Now that we've typed this array, in the second case, we get, I don't know what that is, 20%, 15%, something like that. Okay. So, we have a couple other ways that we can.
So just one question.
Sure.
So is the magic here the difference between when you do the type inference? So in the good arrays, you're doing the type inference earlier on, and so you're still paying the cost of doing it, but you're paying it before the loop. Is that the idea?
So the idea here is when Julia allocates space, when it allocates space to add stuff onto this array, in this case, it does not know the size of anything that's going to be coming next. So it can't like allocate a block of space. In this case, it knows that it's going to be exactly a fixed size. And so it can allocate a bunch of space accordingly. So in this case, it is able to do smart things on our behalf when it knows that it's going to be a name tuple, an array of name tuples with float 64 string.
But it still has to pay an inference cost. Is there a difference between doing it earlier versus later?
Yeah, so if you do it later, if you do it like, so if you were to do it here, like, so one way to like type this array after the fact, R typed would be map identity ARR. And so all this does is just like go through every element and then it tightens the type and it'll be able to see, oh, okay, they're all of this type.
Yeah, I meant something different. I meant like if you took your first val and instead of instantiating the array with the first val inside it, you did the thing you had before with like the float 64 and then the
Oh,
brackets.
oh, like this type of first file.
Yeah, does that make a difference or no?
I'm not sure actually. I think like in this case, it's nice because I don't have to call push separately because push is kind of a resize operation. So like when I instantiate it with a value inside of it, it can, create the array, type it at the same time, and then kind of do this nice thing. And I don't have to do these push calls because these push calls are not optimal. Like I don't like doing push. But sometimes it's really nice when you don't know the size of a thing. In this case, I do know the size, it's 100, but yeah, I think it's better to just like type and place everything all at once when you can. So just, if you can do things jointly at the same time and further type and put things together, then it's wise to do that. I don't know if that helped. Okay. All right. So we can actually make this even better, right? So as I just mentioned, we actually know the length of this array, right? So I don't have to create this array that we can push stuff to. I know that it's going to be length XS. So I'm going to create an array. I'm going to type it by putting in between the curly braces here, the type of whatever our first value is. So this will tell it, hey, I'm going to be putting all these name tuples inside of this array. And then I'm going to leave every element undefined. I'm going to put the first element inside of the array. And then I'm going to go through the rest and just put them inside of the array. No push, just assign them to the inside of this array. Then I'm going to call map reduce. And then I'm going to benchmark it. 14 microseconds compared to 46 microseconds. So this is, like thirded in terms of computation time, right? This is like a very large performance improvement just because we were able to pre-allocate the entirety of the array and statically type the array and tell it was going to be whatever the type of first val is. Okay, so that's huge. That's like a really big performance improvement just from pre-allocation and typing. And we can make this even better. Not a whole lot better, but we can make it a little better. And so this entire function that I called, all we're doing is just mapping something. So if you use map and just do stuff, this will create an array. It'll type it all at once, and it's able to do the, map is a very efficient operation, store everything in array, and then we do the map reduce and call nt.sign, and then we get 13 microseconds rather than 14 on medium. Of course, this is, not you don't always have a function that's so simple that you can call map on it like this, but definitely pre-allocate your arrays, use map when you can, and you'll kind of help alleviate some of this problems that you get from having very abstractly typed arrays. Let's see here. So we often have like these structs that we write to contain results, set model configurations, things like this, right? So Shosh kind of mentioned this in here, where you might actually like concretely typed, you say, okay, I have this struct here called struct with field. It has an A, a B, and a C, and these are float 64, int, and string. This is like kind of fine. Like, if you know for a fact you're only ever going to be putting float 64 int and string in here, this is great, right? This is like not an issue. If you're working with something that auto differentiates across this, you're not going to be receiving a float 64. You're going to be receiving like a forward diff.dual wrapped around a float 64, things like that. So, it's generally considered good form to allow these things to fluctuate a little bit, to allow them to be like, okay, I know it's going to be a floating point number, but is it float 64? It could be like float 32, right? Because there's a lot of like machine learning applications typically go like one way you can get kind of like free speed is like going down to 32-bit operations. And that's a lot faster. It's less precise, but it's also faster. And so you kind of want that to be able to fluctuate, and you want it to like be a float 64 or be a float 32 or float 128 or whatever it is that you want. I don't know if we support float 128, but it's there. So this is good in that this is all concretely typed, but it could be a little more specific. Okay. And so what people do sometimes in this case is they go the opposite direction and they end up abstractly typing the things that go inside of here. So this is a very badly typed struct. This is doing a bad person thing. A now, instead of being float 64, is a real. A real includes float 64, float 32, int 64, int 128, int, int 16, int 8, whatever. Basically anything that's kind of a numeric type that is part of the real line. Integer here is a super type for int. So this is int 64, int 32, etc. And C is unrestricted. It is, colon, any means you can put any type in here. Same thing with D. D, this is equivalent. If you leave it blank, it's equivalent to having type any. So if you have type structs with no type annotations, you're doing a bad person thing. You have implicitly abstractly typed your field, which makes it super slow. So these structs end up being really slow and clunky for the same reason that non-concrete arrays are slow, right? So the solution here is parametric typing. And so parametric types are a way of saying, I know I want this struct to be typed, but I don't know what that type is yet. But I know it's in some family of numbers or family of values. So the way that we do this is we have our type name, then we put curly braces, and then we put the type of our variable. We put some type variable inside of the brackets here. And then we put that type variable to the right here. And so now when we construct this struct type name and we give it a value to assign to field, it will say, oh, okay, we gave it an int 64. So now type variable is equal to int 64 for this type. Now this whole struct is very concretely typed. Okay, I'll give you an example of how this works. So I have this struct called parametric struct, where I have some type variables A, which I'm constraining to be of type, subtype of real. So this permits float 64, float 32, float 16, int 16, whatever. B has to be a subset of int. Oh, this should be integer, sorry. Oh no, can I change it? It's gonna get mad at me. Okay, it worked. And then C is just a variable, but it is implicitly of subtype any. That. And then I'm just going to put whatever the type variable is here, right next to each type. And then note for field 4, I'm actually reusing A. So I'm saying, I don't know what type field 1 and field 4 are, but I know that they both have to be whatever type A ends up being. So they have to be the same. So when I construct this, you'll note that it puts the types inside of the parentheses when we print it out. So this one is float 64, int 64, vector of float 64, which is what it's assigning to type C. And then this one here, that's of type A. So it has to be of this type here. And it may throw an error if I do this. Yeah, so in this case, we're assigning it, I'm trying to put an integer into the 4th spot, but this is a, type int 64, this is float 64. And because the two A's, field 1 and field 4 are restricted to be the same type, it throws an error because, this integer is not the same type. Okay. So this is a really good way to concretely type structs. And let me give you a little demo of how it impacts performance. So I guess I'm not going to have a demo here, but it's basically it ends up being the exact same as when you have type unstable or abstractly typed structs, things like that. So just kind of don't use abstract types in field definitions. That's like the biggest rule that I could come up with. If I see the word integer or the word real or any in any of your field structs, I'll be really grumpy. So either parametrically type them, as we just did, or statically type them, like as in float 64, right? So let me see here. This struct is also fine. It's not very flexible, but it's fine. It's concretely typed, and this is quite fast for Julia's compiler to work with. But you can't really change it as you write new code. Okay. Kind of the next tip here is don't change the types of things during runtime. So if you assign a variable a value, try to change that variable only to other values of the same type. So for example, I don't do stuff like this. So I'm creating a variable called x on top of this function. And then I'm going to go through a bunch of variables in I. I'm just going to draw, a random number 10 times. If the random draw is greater than 0, happens 50% of the time, I'm going to assign it to whatever the random draw is. Oops, sorry, this should be float 64. Right? So now at this line, this is a very bad line because X now is no longer always a string. It is sometimes a float. And that means when you get to the bottom here, it could be either a float or a string, because the other line here creates a string and just kind of appends, whatever the current value is plus the random draw. So let's call Typechanger to see what it looks like. Okay, so in this case, we got a bunch of strings, a bunch of numbers mashed together. We can also just get an actual float 64 if we run this enough times. So this is a very type unstable function because we're mutating the type of a thing. We don't want to be doing that. We want to be very consistent about what types we do. When we call code warn type, we'll see here that X is type unstable. And that means that the return value is type unstable. So this whole function is kind of a pain to work with for Julia. You can also call tracer and it'll give you a bunch of noise in here. A lot of stuff in here is, it's about, I'm not going to go through the trace stuff just because it's like a very long report. But in general, it'll tell you that this function is more or less garbage. Okay. So don't change the types of things during runtime. That's like, this is just like a good programming thing. Yeah, you'll save yourself a bunch of pain in that case. I think probably before I start in this one, we'll take a 5-minute break. Yeah, I think this is probably a good place to pause for a minute. Alrighty. Okay, so we are back and we're going to be talking, kind of diving more into kind of little performance tips. This one is actually like, this is also just like a good practice thing. This is not a Julia specific thing. This is a general programming tip. Having read a lot of very academic code, I know that there's, this thing that people do where they tend to write huge functions that just like accomplish everything they could have possibly imagined. And, I look at them and I'm like, okay, well, you can take this little chunk out where you're like computing this condition or doing this thing and put those in separate functions. So in Julia, what happens when you add, break a big function into lots of little functions, Julia is able to specialize each of those little parts much better. So, some functions, they are going to accept a vector of float 64 and they're going to return a vector of float 64. And you can break those operations apart, and Julia can look at those very specific functions and say, oh, okay, I know exactly all the little tricks and tools I can put inside of this function to make it go fast. So it's also just kind of good form, right? To write a bunch of, write many little kind of well-documented functions that accomplish a very specific thing. And it's much easier to debug these, right? So you can debug one small component much easier than you can a gigantic super function. It's also easier for like, if you give like people like me or somebody else, like a kind of a co-author who works more on like the code side, it's much easier to debug things that are in kind of small chunks because they can ask you like, okay, this function does what again? And then they can kind of help you work through debugging it or making it faster or do anything like that. So it's just like good to do for you and it's good to do for other people. So I have this function here called fill random. This is kind of like, I borrowed a version of this from the performance guide, so this may look familiar to some people who are familiar with the guide. But basically all I'm going to do is I'm going to draw a random Boolean. This is going to be 1 or 0, true or false. So if the random value is true, it's going to allocate an array of float 64 of size n. Otherwise, it's going to allocate a vector of size int with size n. So all it's doing is saying, okay, am I going to have a vector of float 64 or of type int? Then what it's going to do is it's going to go through each of those, each element of this array, and it's going to assign it a random value of whatever the type of v is. So it's either going to be a vector of all float 64s, random float 64s, or random integers. And so what I'm going to do here is I'm just going to benchmark this, and I'm just going to say, give me 1,000 random numbers, either int or float64. Okay. So this, here we can take a look at the actual, the type of this code. So this is a type unstable function, right? Because none of the types of the inputs tell us whether or not this is going to return a float64 or an int. And that's a problem, right? That's what that's like the very definition of type instability. Okay, so it could be a vector of float64, it could be a vector of int64. We don't know, and Julia doesn't know. And so when we benchmark this, we're going to get like 6 microseconds on average, on the median, and we'll put this in kind of context a little bit when we break this function apart. Okay, so the thing I'm going to separate out is actually this part here. It's going to be this part inside of the loop. We know that this v is always going to be type unstable. Let's say we're unwilling to change this, or someone's told us we don't want to change this, but we're actually going to do the filling of this function here. So what I'm going to do is I'm going to define this rfill function, and all it does is it's going to fill each element of v. And this is a mutating function, which is why I've put the exclamation point here. You don't have to, you can leave this on. It doesn't mean anything in Julia, but by convention, if you change the input, which I'm doing right here, you put a exclamation point at the end of the function name. I'm going to find the input type here. I'm just going to annotate it as t, and then I'm going to put this where t thing here. So what that does is it's basically replacing this EL type call. That's basically what that does, is it gets the element type, which is the thing right here, float64. And then I'm just going to call for a random version, a random number of whatever the type of t is. So that's going to be either float64 or int. Okay. And then I'm going to call rfill instead of doing this for loop inside, and this will do the filling on our behalf. All right. And so let's benchmark this now. And so while that's happening, I want to go back to our example here and note that we have 6.46 microseconds. This one's a little bit shorter at 5.536. So we haven't gotten rid of all of this, type instability problems that we had, right? This function is still very type unstable. However, we've been able to put a little function barrier inside that makes it so that this part is actually very type stable. Because, when you give it a vector v, you know that it's everything inside of here is going to be conditional on type t. So this function here is type stable. This one is not. So when you're able to break things into little function barriers, Julia is able to say, oh, okay, I know that this one here is like very type stable, and I can make this very fast on your behalf. Whereas, this one here is just kind of going to suck. We can fix it a couple other ways, and even break this apart another way. Yeah, but I'll leave that off to the side for now. But as long as you kind of break more and more components of your function into very well-defined chunks, you can start eliminating type instability. And it'll also make it a lot easier for you to detect where type instability shows up, because it'll show you in code warn type, oh, it's coming in from this particular component, right? So at code warn type, fill random compartment, for example. It'll tell us v is the thing that is not well typed, but it has nothing to do with rfill. And if I do rfill with 0's 10, right? This is a float64 type. This one is also this one is concretely typed, right? Because it returns nothing. Okay. All right. So I'm also going to kind of segue here into kind of like the next big weird thing that you can end up doing in Julia. So this is talking about memory allocations, and like this is a thing that like people hand wave around, and they're like, well, your memory allocations are really high, or you're taking up a lot of space, or things like that, right? And nobody actually really talks about what it is, especially if you're in kind of scientific or like academic computing. You're just like aware that it's like a thing that's costly, but you don't quite know why. And so I'm going to kind of hope that I can give you a little more intuition about it. Okay. So I'm going to start with this truth here. Memory allocation is costly for your machine to do. It's a task that it has to complete. It basically has to draw a box inside of your memory, your RAM, and put space for it and put things into that box. Okay. So when you create a new object in memory, Julia has to go find or make space for that thing in RAM. And that's costly. It takes time. You have to, if there's already a bunch of space, sometimes you have to run the garbage collector to clear space and put a new thing there. Sometimes you have to move things around in memory. It's just like a costly thing to shuffle around. Okay. The important thing here is that there's two types of memory inside of most programming languages, and this is not a Julia thing. There's this thing called the stack and the heap, and this appears in like basically all programming languages. They both do two different types of things. So the stack is short-term memory. This is like fast, I'll get to this in a second. I just need to put it off to the side and store it for half a second and pull it back off in a minute. You can think of short-term memory as like a stack of plates. So when you put a new object onto the stack, you put it on top. When you take things off the stack, you remove them from the top first. So this is a LIFO type memory thing. So frequent things that you use a lot, they go on top of the stack. You can put them on and pop them off, put them on, pop them off. And the stack is usually for really small things that you use frequently, right? This is the fast type of memory. This, faster relative to the heap. The heap is like a bookshelf. You don't cover up other things. You don't put books on top of books. You stack them horizontally. The problem with a bookshelf is you have to like read the book titles or like go look at the Dewey Decimal System to find where the books are. So you can put really big things on the heap, but sometimes they're hard to find. You have to take them down off the bookshelf. Maybe you need a ladder. Like it's just kind of more costly to put things on and take them off the heap. Okay, so stack, fast, small. Heap is like big and kind of slower. So where your thing goes when you create a new object or struct or type is kind of at the compiler's discretion. But in general, there's a couple of rules. So things that typically go on the heap are arrays, dictionaries, mutable structs, things like that. These are like relatively big objects that are kind of mutable that you need to like swap in and out or go access later. You know that you're going to have them a long time, things like that. Things that go on the stack are non-mutable structs, typically single values. So if you just have like a single integer or a single float 64, name tuples, static arrays, things like that. If any of these things end up being really, really big, they may be too big for the stack, and so they end up going on the heap instead. And in some cases, you can have arrays that the compiler decides are small enough to go on the stack, et cetera. This, you can kind of cross in between, but this is one general way to think about what's heap and what's stack. So anything can end up in either the stack or the heap. So why does it matter whether something is on the heap or on the stack? So heap allocation is slower than a stack allocation. You have to put it on, you have to put it in the stack, you have to find a space in the bookshelf for it, you have to go look it up. So it's harder and slower to kind of work with heap allocated variables. And so stack allocation tends to be really fast. So sometimes it's worth keeping in mind whether something is going to end up on the heap. So to show you how this works, I'm going to use the static arrays package. Static arrays is not part of Julia base, so you have to go install it if you want to follow along. So you can add that with, import pkg, pkg.add static arrays, like that. And that'll add that to your call if you need to. Okay, so I'm just going to import static arrays. And static arrays are really nice because they're strongly typed in their size. So the compiler knows exactly how big a static array is going to be. And so it can allocate a very specific size for it. It doesn't have to do this like, with conventional arrays. You can expand them, you can shrink them, you can do all kinds of things that change their size. So maybe it's better that they're on the heap where they can have room to grow. If it's fixed size, there's only 100 things in it, then maybe it's better to put it in the stack because that's quick. So I'm going to write this kind of really dumb function. All it does is accept an array m. It's going to calculate the product. It's just going to multiply m times m transpose, and then we're going to invert it, and then we're going to calculate the LU factorization of this inverse matrix product. Okay, so this is kind of a nice function to experiment with. So I'm going to set the dimensionality here to 10. So k is just going to be equal to 10. So I'm going to be working with 10 by 10 arrays. So m here is just going to be a bunch of random normals with size kk. So this will be a 10 by 10 array of random normals. And then I'm going to create a static array using the S matrix struct from static arrays. And then in the two squiggly brackets in between, I'm going to put kk, which tells me exactly what the size is of this array. So I'm telling you, please create an array. It's exactly 10 by 10. And here's the array I'm giving you, which is a 10 by 10 array. So I'm basically wrapping m inside of this static array. When I time this, I'm calling it with the exact same function because, all I'm doing is changing the type of the input. All these types will dispatch on the static array types, which are all, we know the size of them. We can see that we get 7 allocations when we work with the normal arrays. This is just a very plain matrix. We get 7 allocations. This is the number of times we had to do a heap allocation. And this is how much memory got put onto the heap. So 8.03 kilobytes. And when we do benchmarking for the static array, we notice, first of all, it's much quicker because we know the exact size of these arrays. Static arrays generally end up being free speed if you know the size of your arrays. And we get 0 allocations. Of course, that means that doesn't mean there's no memory moving around. It means there's no memory moving to the heap. So anytime you see anything in here when you call at b time or whatever, and you see a number of allocations, that means the number of times something went to the heap. So this is saying we're putting nothing on the heap when we do this array, when we do this call. Everything's going to the stack. And so we end up not having to do any kind of heap lookups, any kind of heap placing, no allocations in the heap. That's really ends up being quite fast. So one of the nice benefits of using static arrays or kind of immutable types is that they tend to be more stack allocated, and then you incur less speed penalties from doing heap allocations. Okay, so this is kind of a very academic, complicated example, but try to put things on the stack, use more immutable, concretely typed, small, known size things rather than things that can grow forever, like dicts or strings or arrays. Okay, which tend to go on the heap. Okay, so you can sometimes get performance gains from working with stack allocated immutable types. But it's kind of, it's hard for me to predict ex ante. I know some people have a better sense about whether things are going to go on the stack, whether they're going on the heap, how to write their code in such a way as to enforce going on the stack or going on the heap. I'm still very bad at it, even though you can get some pretty crazy performance improvements from working with it. So this is kind of why I recommend people don't use mutable structs, because mutable structs tend to end up on the heap. In some cases, it's cheaper to stack allocate a new immutable struct rather than modify a heap allocated mutable struct. And I'll cook up a quick little example for you. There's two structs here, 2 types I've defined. that are basically the exact same, that the only difference is there's a mutable keyword in front of one. So when the compiler sees this, it'll be like, oh, okay, somebody's going to keep changing this thing. I guess I'll put this on the heap. In general, not always the case. And then I'm going to define 2 functions here. So the first one is just going to double this immutable struct. All it's going to do is extract. It's going to accept a previous version of an immutable version, and it'll return a new one, a new fixed one, because we can't change any of the fields. all we're going to do is extract A, multiply that by 2, B, multiply that by 2, so on and so forth. This will give us a new struct when we call double immutable. The mutable version of this struct, remember I put in the exclamation point here, is going to work with a mutable version of the struct. And it's just going to multiply everything by 2. And we can return M. We don't have to, but I'm going to return M anyway. And then I'm very lazy here, and I've defined a version without the exclamation point, just so that I can kind of call them in the same function later on. So don't get mad at me. I'm doing a thing I didn't want to do, but this is technically a mutating function. Okay, so I've defined this mult double function here, and all it does is accept some value, which is either mutable or immutable, and then an integer, which is how many times I want to double something. So I'm just going to recursively call double on one of these things. So, and then return whatever the last value is. So I'm going to define an immutable version and a mutable version. I'm going to give them the exact same values. And then I'm going to give them some timing. And this one actually ends up having more or less the same amount of, this is like a very bad example, right? It's like a case where I was not able to like perfectly predict whether something was going to end up on the stack or the heap. But in general, they tend to have very similar performance. And the immutable one is maybe slightly quicker with a little bit fewer allocations. In some cases, I think you can cook up examples where this ends up being like a lot bigger of a concern. But I haven't been able to find one, like a reliable one.
Cameron, can you give it? I still don't have a good intuition for why mutable versus immutable would make a difference if you're just taking it as an input. Like, I understand the idea that if you have an immutable object, then type inferencing is much faster because you know for sure what is that the only thing that's going on? Because you're ultimately still creating a new object when you do your computation, right?
You're right. You are creating a new object, right? And that goes on, if you're creating something and it ends up going on the stack, then that's like fairly cheap, right? It's, it's not free, but it's not, it's relatively cheap as compared to putting it onto the heap. Accepting it as an input is a good question. I don't know that I have a good sense of like whether or not it's cheaper to be in the to be an input, because if it's stack allocated, then potentially if it's a stack allocated input, then potentially it's really easy to access it really quick. But that may not necessarily be the case. So I don't know that I have a good answer to that question. I guess my concern is really more with the return value, or like the thing that you're putting inside of the structs. So like, modifying a mutable struct a lot can end up being fairly costly because you have to keep going to the heap lookup, keep doing the heap lookup every time. Whereas if it's stack allocated, you're like, okay, well, I'm taking in one immutable struct and then I'm returning a new immutable struct that's the exact same size. So, I can just put it right back on the stack where the other one was.
So is the intuition for the trade-off basically the difference between doing index lookups for the mutable struct versus reallocating new space for the immutables? Yeah,
basically. And I don't know that I have a good sense of like when and where those things end up being faster. So
maybe if there's some sort of like struct that's very complicated and has like lots of other features that aren't changing but need to be replicated.
Yeah, maybe. I guess I'm not super sure. I was trying to cook up a much better example for this, but I ended up with like them having like more or less the same amount of allocations. They're both going to the heap. And the immutable struct ends up being like actually a little slower in this example.
Yeah. But your structs just have a bunch of numbers. If your struct had like arrays of arrays of arrays, and there was like one element that was changing, probably.
Yeah, maybe. Yeah, I don't know. I don't have a good sense. I wish I had more time to kind of dig into this one because I think it's kind of important and interesting, but I haven't been able to like cook up an example where one is like vastly superior to the other. Even though kind of anecdotally, it seems like the Julia community is like, yeah, it's kind of like a big issue when it's like mutable or immutable. Just haven't seen a lot of evidence. Okay. So the kind of next part here is a weird one. So this is really familiar to people if you come from C or Fortran, or you have like a very like classical computer science understanding. So this is called column order versus row order. So when Julia puts arrays in memory, values in the same column are next to each other. So it basically, you can think of it as taking arrays and taking columns and stacking them all on top of each other. So it's really easy for you to go to the next row because you know, oh, okay, it's just the next address down. I'm just going to shift 64 bits. I know that I'm at the next float point. Whereas if you're in row, if you're trying to go to the next row within a column, or going to the next column within a row, you have to shift by 64 bits times whatever the length of your array is to go to the next spot. So you have to do this huge jump if you're trying to go to the next column within a row. Okay. So to give you an example of this, and I did not realize until I made this example how crazy important this is. So I've just created a function called rowSum and a function called callSum. They accept an array called M, and all they do is add up every single element in the array. The only difference is that one does it, the inner loop is columns, so it stays within the row and goes across columns, goes to the next row, goes across columns. And then callSum, all it does is stay within the column and go all the way down the rows. CallSum here is the one that we would predict to be faster because the thing, going from row to row within a column is the fast one. Okay, so this is what you should kind of expect, is that callSum should be faster. All right, and so I'm just going to create a 10K by 10K array. So this is huge. I'm making this one really big just so we can kind of get an example. While it's going here, I just want to like reiterate, there's like really no difference in here. You would think that this should not matter that much, right? Actually here, I might just call this with like normal time. Unless it takes a second here. I should not have done this with so big an array. I was all gung-ho about this. Okay. There it is, perfect. Okay, I want to highlight how incredible this is. This is 177 milliseconds doing callSum. This is the one that follows the order of the arrays in memory. This is the one we thought was going to be fast, 177 milliseconds. This one is so rowSum, where you go, across within a row, where you're going against the column order, is 1.809 seconds, not milliseconds. This is like so many orders of magnitude slower that it's like not even funny. So if you're doing something where you're going through an array and you have an option to go across rows or columns first, put columns first. That's like, columns should be on the outer side of your loop. And if you can design your arrays in such a way that that is relevant to you, then you should probably consider doing it. So, put rows in your inner loop, columns in your outer loop. That's like the big example of how to do this. And in case you ever forget, I want to show you an example, a way that you can recover whether or not it's column order or row order. So for example, here I'm going to create an array that is 1, 2, 3, 4. If you just do an array with a single colon inside of the brackets, it'll show you the order of those numbers in memory. So it goes 1, 3, 2, 4. So this is a good way of trying to understand how things are laid out in your memory, in case you forget. And that's free speed. Okay. So kind of the next thing here I'm going to do is talk about compiler annotations. So sometimes you can give the compiler really helpful hints to remove things like bounds checking, or tell the compiler that something can be like cheaply parallelized. And these are just macros that you put inside of your function that can actually end up massively improving the speed of various functions. And I'll go through some of the common ones here. So this one you tend to see a lot in, like if you're going on like Stack Overflow or you're in the Julia discourse, you might see @inbounds. And then you're like, what is @inbounds? I don't understand what that means. basically what that means is you put inbounds in front of something to tell Julia that it does not have to do any bounds checking. And bounds checking is what you do to make sure that you're not going to get the 11th item of a 10 element array. This is a really good protection to have, because if you say, get me the 11th item of a 10th element array, basically what you end up doing is just kind of like, if you have no bounds checking, you're basically just accessing random memory that's inside of your computer. This is really bad. Like, this is, these numbers could just be like totally nonsensical. You could get mysterious errors, like, and this may fail silently if you're not doing bounds checking. So for really simple loops, Julia can figure out sometimes you're within bounds and it's not going to check for you. And sometimes like it'll add this at inbounds of the compiler for you. Sometimes it can't tell whether or not something is strictly inbounds, and it needs to have it disabled for you. So only use at inbounds when you know for a fact that you're accessing the correct number of elements in an array, that you're not going to go too far outside of the bounds of the array. So you can get really stupid results if you don't do this. All right. So I've written, so I've written two functions here. This one here is just, all it does is it takes two arrays. It's going to assert that they're the same size. And I'm going to create an array of the same size. I'm going to create a sum value here. This is just going to be the 0, the element type of A. So I'm going to add the cross product of the product of every element in A and B. So the important thing here is Julia does not necessarily know, even though we've asserted this up here, it can't always determine that B is always going to be in bounds. So it's going to do bounds checking on BI. For I in each index A, this is like a thing that says, oh, okay, I don't really need to do bounds checking on A because, by definition, I'm only ever going to go 1, 2, 3, 4, all the way to the size of A. Then I'm just going to add them all to the sum. If I have an inbound, if I add the at inbounds here, now I'm saying, okay, I know for a fact that I is never going to go below 0, and it's never going to go above the length of B. Every single I that I give this is going to be well-defined. There's always going to be an element of B. So I'm like playing with fire a little bit, but I'm smart and I can handle it. Okay, so now I'm going to create a 10K by 10K array, 2 of them to be exact. These are the ones I'm going to multiply and add together. And so when I benchmark these, some prod normal and some prod inbounds, you note that this is like a fairly sizable increase. This is like 15 to 20% when doing it without the inbounds check is 15 to 20% slower, because this inbounds check is like kind of a pain. So this is a little bit of free speed. We've gotten like a pretty good bump, but we can do better. Like, we can do a lot better, actually. The inbounds check free speed if you know that it's within bounds. So sometimes it's a good idea to add to things. The next one is at Simdi. So Simdi is it stands for single instruction, multiple data. And I talked about this like kind of a little bit in the parallelization lecture. But basically what you do is you say, dear CPU, I have one thing I need you to do, but I need you to do it to a lot of different things. And when you tell your processor to do Simdi stuff, your processor doesn't have to use up a bunch of different instructions for all the different data points it's going to use. It stores just the one instruction and it just runs all the data through it. When you use at Simdi, you're telling the compiler that the order of your operations can be done more or less randomly. You're saying, please, you can shuffle this around, do it however you need to. I just need all of these things to be done and kind of put in the right place at the end. So if you're using at Simdi, you're telling the compiler it's okay that these things will get shuffled around. Do not do time series in Simdi, right? If you need to do like lagged T, do not do this. Every single element of your for loop has to be independent of all of the others. So all I'm going to do is put at Simdi in front of the for loop. This is telling the compiler, hey, it's okay to shuffle this around. All right. Now, when I time this, I get 15 microseconds, which is, we've shaved off about a microsecond and a half from the inbounds one. This is still a little bit faster than the other one, but this is, still pretty damn good. 1 microsecond shaved off is really awesome if you're doing this millions or billions of times. Okay. And we can still do even better. We can combine both of these. We can say at Simdi, so please, this is a single instruction, multiple data type situation. And I know that everything is in bounds. You don't have to do any bounds checking. Always do this cautiously. If you're like start combining performance annotations, like be really, really cautious. Like go actually read the docs for Simdi and go read the docs for inbounds and make sure that I is defined everywhere for B. Otherwise, this is going to be a huge pain. Now we get 2.5 microseconds.
Cameron, is it safe to assume that anywhere where you think you can do parallelization, you can also do inbounds in Simdi?
Yes, probably, right? If you're doing like threads.threads, like chances are you could get some good speed from doing that.
But in terms of like safety, right? Like this, is it the same consideration?
They're like slightly different considerations, right? Because like with, if you're doing like thread distributed parallelization, you have to work a lot with thread safety and make sure that your threads are not stepping over each other. With Simdi, you don't actually really have to worry about thread safety. You really have to worry more about like, is the structure of your loop actually amenable to doing Simdi stuff? And in some cases it isn't. And the docs.
What's the difference? Because the way that you explained it is just about shuffling the order, which I understood as shuffling the order of I's.
It's not actually, it is not necessary that it shuffles the order, but it is basically what tends to happen. You're basically telling your CPU, hey, I just want you to do this one thing, just, add these two numbers together and multiply these together and add them together. And then you're just going to basically open a fire hose and shove a bunch of data through. So sometimes it gets jumbled while that's happening. When you're doing multiple threads are like, they have like different, they just have a lot of like extra considerations to worry about. So this is, Simdi is a very single-threaded kind of
so so I'm still not really understanding. Could you give an example of the kind of thing that could go wrong with Simdi?
Yeah. So here, so if you have a Simdi loop that's like extremely complicated, it may not actually be amenable. Oh, actually, there's like a good guideline here. I should have read this before I brought it up. Yeah, here. Yeah, so they basically give you a bunch of guidelines here. So the loop has to be kind of an innermost loop. You want these to be like really uncomplicated operations inside of Simdi. And you can't like cross-talk to each other. With multi-threaded, you can actually cross-talk to other elements in the thread, but you just have to be a little more straightforward about it. Like at Simdi is like a super low-level CPU operation that has to be really uncomplicated, like basically arithmetic operations, that kind of thing. Like it's meant to be like, if you're like zipping multiple numbers up together, like I don't think it's going to be wrong per se. I don't know that that's necessarily true, but it is a low-level operation that is intended to kind of like do a very basic task. If you need to be very complicated and do like lots of operations and calculate eigenvalues or something within a Simdi thing, it's probably not like a good application for that. But I don't really have like a good sense of like when it is that it causes something to be wrong.
Okay. I mean, like the easy example I have in my mind is like if I want to like compute a moment of something, so I need to do some sort of like complicated matrix multiplication where it matters that the indices of one matrix correspond to the indices of a different matrix, but I don't really care what order they're in. Then maybe
that's a good application.
And then like multi-threading would also work because all of these things are additive to some degree.
Yeah, I think that's actually a pretty good use case for Simdi, just because that's like that's kind of a dumb operation. And in some cases, doing this like spinning up new threads is actually, or talking to multiple threads is kind of expensive. Whereas Simdi is like a very direct line to the CPU. Hey, you have one thing to do it with these many things.
Right. And if I cared about actually preserving the matrix, then I wouldn't use it because it might reshuffle the order. But if all I care about
it'll keep the order at the end of the return value, but it doesn't when it's being calculated. I equals 5 may be calculated before I equals 1.
Sure.
But at the end, they'll all kind of be in the right order, depending on where you put them.
Okay.
Okay. All right. The next step here, this is like a big offender for a lot of people. Don't do stuff to global variables. In like Python and R and stuff, this just like happens all the time. Like, because scoping rules, especially in R, are just like kind of like nonsensical and very permissive. And so if you come from an R world, you may tend to do stuff like this, where you say, oh, okay, I'm just going to like create a variable. I want to use this somewhere else. And so you create this variable, this string that just says, I'm a bad global variable user. And then you may have a function that accesses X. And this is like kind of fine in R, right? Because like everything is just kind of like, R is like just like a hand wavy, like, yeah, I guess that's fine kind of language. Julia is not that kind of language. It's, it works, but it's going to be slow and it's going to suck a little bit. And you need to be aware of that whenever you do this kind of global variable stuff. So to give you a baseline, this is 48 nanoseconds. All we're doing is going to grab the global variable and we're going to smush please be kind to me at the end of it. Okay. And so this is, this is a super simple function. So there's 2 solutions to doing this global variable thing that you did right here, which I don't like. The first one is to annotate your global variable with const, which is a keyword. If you put const in front of a global variable, it says, I'm not going to change this variable, I promise. It's going to be the same type. And so Julia can look at this constant global variable and say, okay, it's a string. They told me they weren't going to change it. I can treat everything that talks to this as a string, and I don't have to worry about other functions changing it. Alternatively, you can pass the variable in as an argument to the function. This benefits from all the stuff that you get from when Julia specializes a function. And this is kind of probably the more robust one. But if you're really only, if you just need one variable to be available everywhere, you can put a const in front of it, and that'll make it okay. Okay, so the first way to do this is just put a constant in front of it, and then we get 29 nanoseconds. So for sense of scale here, that's almost halved in terms of speed, just because now it doesn't have to access this global variable, which is untyped. Now it's typed and it's a string. Okay, so this is a good way to do this. The alternative way is just to pass it in as an argument and just remove the global variable entirely, and this gives you a similar performance speed up. But it can matter a lot more if you're doing something more complicated than this. Just don't do global variable stuff. That's just kind of a big thing. Okay, that's a super simple one, really, really low hanging fruit. Just don't do it. Only friends help friends, not allocate global variables. One of the other things I want to get to here is about in-place operations. I talked about this, a little bit before, but nothing really in detail. There's a bunch of operations in Julia where you can just add an exclamation point to the end of the function name, and it uses whatever you give it. It just changes the thing that you give it to have the answer inside. Or you can pre-allocate a buffer, give the buffer to the function, and it'll store everything in the buffer. This is really nice because you don't have to keep doing reallocation, right? You just change whatever you give it, the function just changes whatever you give it, or it puts it in a buffer, and you can just reuse the buffer if you're calling this operation, millions or billions of times. You can avoid a bunch of allocations. So a common way of doing this is what's called in-place operations. And in-place operations modify their input or modify an input rather than returning a new object in memory. So in-place operations, rather than doing x equals a times b, we can pre-allocate x and just call mul with an exclamation point, which says multiply a times b and put it in x. And this can keep allocations down. Not always. Sometimes the compiler is very good at handling this and like putting this on the stack. But if you have like you're doing a bunch of heap allocation stuff and you notice memory allocations are way up, maybe you can try to use kind of buffered variables. So this is not always free speed, but sometimes it is. And you should probably benchmark your application to see if doing these in-place operations can help, because sometimes they're a little more complicated and a little bit of a pain, and it's not always obvious that they give you like massive speed improvements. So here I just created a function called eigtimer. All it does is it creates a 50 by 50 matrix. The first one, it calls the eigenvalues of M. This is the non-in-place version of this. And then eigenvalues with the exclamation point actually ends up modifying M a whole bunch. It doesn't store the eigenvalues inside of M, but it returns them, and it'll mutate M inside while it's working on the problem to use M as a workspace. And it'll restore M at the end to whatever the value is. So both of these end up returning the same value. At the end of it, M is always the same value. But this one just happens to have a lot more memory space to work with, and it doesn't have to do as much memory work. And so in this case, eigenvalues just ends up being cheaper, like by quite a bit. So, you know, in a lot of cases, you can just by adding the exclamation point or looking up the exclamation point version of something, you can get some pretty significant performance improvements. And this is the case for a lot of linear algebra functions inside of Julia. So if you end up doing a lot of linear algebra, you know, I would look up to see if there's mutating versions or in-place operations that give you a bunch of nice speed improvements. Okay. This one, I'll actually skip this one because it's not as super important. This one is like definitely important. So you may not have heard the word closure. A closure is a function that captures a variable outside of the scope of that function. I'll show you an example of what that looks like. So AB mult here, this is taken from the Julia docs. It's a very, very handy little guide here. All it does is accept an integer r. If r is less than 0, it flips the sign of r. And then we create a new anonymous function, right? This is an anonymous function. It's equivalent to if I wrote f of x equals x times r, right? In either case, this r here comes from outside of this function, right? We're not passing it in as an argument. We're only passing x as an argument, but we're using x from somewhere else. And in general, this r happens to come from outside of this function. So Julia has an incredibly hard time in this function in particular, this first cell, figuring out what the type of r is. And this closure ends up being a huge pain. So when I call AB mult 3, this returns a new function, and then I'm going to call that new function with 2, right? So I'm giving it 3, it's going to look, it's going to say, okay, r is greater than 0, so I'm not going to do anything. I'll return the closure, which is 3 times whatever the input I give it is. And so this should return 6. And this takes 56 nanoseconds to do this whole thing, to make the new function and call it. This is a very type unstable situation up here, just because we're doing all this operations over here. We don't know, this r comes from outside of the function, and we don't know what exactly the type is. Other people could mess with it. And so this closure ends up being a bit of a pain to work with. What we can do is actually take r, we redefine r as r0, and then we just copy it into a local variable into this inside of the AB mult 2 function, and we annotate the type as int. And then we work with r rather than r0, because now r0 came from outside of the function, r is local to our function. And so when the closure captures r, it's working with something that's you know, not outside of the scope of this entire AB mult 2 function. So this one ends up being so much faster, right? This is, you know, little over 10x improvement in speed, just because now it knows exactly the type of r, and it knows it's not going to get messed with. We can do even better than that. So this AB mult 3 function, we're just going to accept an r, and we're going to go back to the original version of AB mult 2, right? This is all the stuff where we're going to flip the sign. Now we're going to use let. And so what let does is it takes something from outside the function and it hard scopes it inside of this function, inside of this closure. So this closure now has access to R as a local variable inside of F. So F no longer depends on R, the outside version of R. It only depends on the R that's inside of this function. It's now copied to F and we don't have to care about it. It's now very concretely typed and this closure is very well defined. Now we get 0.038 nanoseconds, right? That's massive improvement over this. Just by using this let block to copy a local value, a local variable inside of the closure. So a common thing that you might do is maybe you're defining an optimization function where you're trying to vary the parameters of something. And oftentimes you end up closing around a variable that's outside of that. Generally, you should probably use this let block to kind of capture those variables and make it so that this goes away. You may or may not have to do this in future versions of Julia. They're trying to get this into the compiler. I don't know the status of it exactly, but you may or may not need to do this in the future. So just kind of keep that in mind.
Cameron, is there any are there any worries with respect to the naming conventions here? Like, is there any way that the R is equal to R?
Nah, it'll use the locally scoped version of it rather than the outer scope version of it. So that'll save you some headaches. I think probably with the last little bit here, I'm going to show you how to use a profiler. So this is like a very advanced kind of performance tool. So we often don't know how much time we're spending in different places in our program. So which line is the slowest? Which one takes the longest to compute? Oftentimes we don't know. It's hard to tell ahead of time. So common way that programmers debug their code or not debug, but check where the performance is, where they can get the most gains from trying to speed things up, is to use a profiler. And so a statistical profiler just, every couple of milliseconds or nanoseconds or whatever, checks to see where you are in the program. And it checks the whole call stack. And so when you look at those counts, you can see, okay, well, 50 out of 100 was in this, 50 out of 100 times we checked, we were in this line, which means that line is 50% of the time that we're doing the compute. So maybe we can make that function a little bit faster and then we have the biggest marginal gains. So that's how you kind of use a profiler. So I'm going to import this profile package. This comes with Julia. You don't have to install this, so you can just call using on it and bring it in. Then I have this function called weird inverse, accepts a matrix. I'm going to copy a result because I'm going to modify it a bunch of times. And then I'm basically going to end up storing all the eigenvalues. So what I'm going to do is I'm going to invert the matrix, multiply it by 2, add the result, add the inverted results to the result, and then store the eigenvalues of that result. And then I'm going to do that n times. By default, that's 10 times. Okay, so this is kind of like a weird linear algebra function. And you may not know which of these 3 lines is going to be the costliest. Matrix inversions can be quite expensive, depending on the size of your array, but it's not clear whether the eigenvalues of the inversion is going to be the more costly thing. So what I'm going to do here, let me actually get out of this, this view here so we can actually read this a little easier. I'm going to create a 10 by 10 array, assign that to A, and then I'm going to call profile.clear. I do that just before I start profiling something because it'll accumulate everything inside of your profile buffer and it'll stay there until you clear it. So if you're rerunning the same line over and over and reprofiling, you want to clear just before you call this at profile thing so there's no GAC left over from the previous run. You can call profile.init to set how many, basically the seconds delay between observation points. So for here, I'm doing 1e minus 8 is the delay in between observations. And then I'm going to call weird inverse just by itself so that it compiles. I want the Julia compiler to actually go look into this function and run it the first time so I don't have to deal with the compilation time when I profile it. And then I'm just going to put at profile inside of my function. Now this will go through the function, it'll sample it a bunch of times, and then it'll print out, and then I can print out the information, profile.print, and then I've specified the keyword argument min count equals 3 to require that, if I'm at some weird tiny little line only one time or 2 times, I don't want to see it in the printout. So you end up getting this kind of tree diagram here, and there's another format here, but this one's pretty nice. And this says 105 times we were at base.task.jl. This is like the top level thing that ends up calling all of your code. So there's a bunch of things in here that are just kind of like at the very top level that run always. And then we realized 104 times we were inside of this weird inverse line, the top line call, and then we can look at all of the lines underneath it. So 24 of those 104 times, we were in line 12 of weird inverse, which is this one here. We're doing 2 times the inverse. 20 times we were inside, we were doing with that, 20 of those 24 times we were in inverse. So it's just, most of the cost in that line is just from doing the inverse. 12 of the 104 times we were in line 13, adding the inverse to the result. And then lastly, 65 of the 104 times, so this is the bulk of it, we were calculating the eigenvalues. Okay, so this is actually kind of a pain to read. I don't particularly enjoy reading this. I may have to actually compile everything here. Sorry, this may have been from a previous run. No. Oh, yeah, sorry. All right, here, let me run through this here. Okay, so there's a lovely function called profile view, and profile view, all it does is it basically takes this information and it plots it out into what's called a flame graph. So this visualizes the entire stack of information. So at the baseline level, this is a thing that basically everything is sitting on top of. So this is the entire function call basically, from start to finish. And we can mouse over it and see a little bit. I know it's kind of hard to see. The text is super small on my monitor because it's just a pain. But this one says boot.jl eval. So this is it actually evaluating the code that we ran. This line here is weird inverse. So everything above this green bar is all the code that we ran to calculate weird inverse. One line above, we can see all the lines within weird inverse we were stopped at. So as we can see before, most of it, more than half of the time, we were calculating weird inverse. Line 14, which is where we calculate the eigenvalues. And you can see from the red that is a type unstable function. This it ends up being quite nice. It colors things for you that it thinks are slow. So we can see here, if we were programming this, we'd be like, oh, okay, how can we make the eigenvalues calculation a little faster? And if we can't, then we can go to the next big thing, which is line 12, which is the initial inverse, and multiplying it by 2.
Cameron, right. in the profile, it just gives you the number of times that things were being run, right? It doesn't give you the actual duration of each call.
Yeah, that's correct. The idea here is that if you increase the tightness, how often you sample, that roughly approximates the proportion of time that you spend in any particular call.
And does the profile picture, is that capturing a deeper time dimension, or is that also still capturing the number of times that you run a call?
Number of times, so it's all relative clock time, basically, which is actually super handy, right? Because you kind of want to know, like, is this function like 50% of all of my runtime? If so, then yeah, that's the thing I want to focus on.
And I guess you could do the beat time call or something like that for specific things if you're curious.
Yeah, exactly. And that'll give you like clock time or wall time, which is maybe a little more informative. Okay, that is all I have. Thank you very much, everybody. I hope you have a kind of nice time, and I guess I'll see you for the next session.